Welcome back to Physics Fundamentals. In this video, we're going to be talking about momentum. Before we can get there, though, we need to start a little bit further back and think about how we've been dealing with forces up until this point. We have looked at the situation of forces acting on an object in equilibrium, where the forces try to balance each other out. We've looked at the situation where the forces are not in equilibrium, which causes an acceleration. And we've thought about how we can use energy as a way of describing these things without having to get to the details of forces. But in all of these cases, we have assumed that the forces have been constant and consistent. What if that wasn't the case? What if we had a force that acted on an object for only a brief period of time? For example, striking a baseball with a baseball bat. Right? The pitcher throws the ball, imparting some force on it. The baseball is now moving at a velocity as imparted by the pitcher. The batter swings at the baseball, makes contact, and the baseball stops moving towards the batter and starts moving in the other direction. In the few moments that the ball is in contact with the bat, all of this exchange happens, and then the ball starts moving again in a different way. So we have a concept called impulse, which measures that very brief interaction between an object and a force. Impulse is force multiplied by time. Well, before we get into the details of how this works and how it can be useful, or I guess as a way of getting to those details, let's think about what this means in terms of units. We have measured forces in newtons, and we have measured time in seconds. Nothing too surprising there. A newton itself is a kilogram meter per second squared. And if you multiply kilogram meter per second squared times second, one of those seconds will cancel out, and you're left with kilogram meter per second. This is the unit of impulse. It's a bit of a mouthful, but not quite as much as some of the other units we've talked about. And so for that reason, the official designation of this unit is still the kilogram meter per second. Recently, there has been a push to try to give this unit a name. They want to call it the nother, which would be abbreviated NR. Personally, I hate this simply because NR looks too much like N, and I know I'll make a mistake. That said, I think it's worth mentioning Emmy Noether, the German mathematician and physicist for whom this unit is proposed to be named. Albert Einstein referred to her as one of the most important figures in the development of mathematical physics. Her work is the cornerstone of the modern understanding of conservation laws, and we are going to get to a conservation law using these units by the end of the video. So if you don't want to write out kilogram meter per second, you think that that's a little bit too much, there is this other unit that people are trying to make exist. I have not yet seen a textbook using it, but there's a lot of talk of it in scientific communities, and who knows, maybe 15 years from now it will finally get adopted. All right, but I'll stick with the kilogram meter per second, and looking at that actually gives me the next place I want to go. Because when I see kilogram meter per second, I immediately look at that and say, oh, I've got kilograms, I've got meters per second. Kilograms are a measure of mass, and meters per second are a measure of velocity. So if we multiply a mass times a velocity, we should get the same kind of measure as an impulse, a force times a time. The quantity, mass times velocity, is what we refer to as momentum. For reasons that will make no sense to me ever, the variable for momentum is p. For our purposes in this video, I'm going to deal with momentum in just one dimension, just to make life a little bit easier. But I do want to mention that in general, momentum is a vector and velocity is a vector. You can deal with these things in two dimensions. It works, it uses all the same rules, but it makes the situations a little bit harder to model, so we'll stick with one dimension for right now. Right. One of the more on-the-nose names in science, the impulse momentum theorem, is our claim that these things are in fact related. And it simply says that the impulse acting on an object is equal to the final momentum minus the initial momentum. So impulse causes a change in momentum. Putting some numbers to the example I talked about earlier. A baseball with a mass of 0.145 kilograms reaches the batter with an initial velocity of 38.0 meters per second. The batter connects, drives the ball out to the field. It now has a velocity 47 meters per second. For anyone curious, those numbers are in the 38 meters per second is something like 75 or 80 miles an hour, and 47 is like 85 or 90 miles per hour, somewhere in that general vicinity. I'm sorry, 90 to 95 for 47. Somewhere thereabouts. I didn't do the calculation, but it's a little bit more than double to go from meters per second to miles per hour, so it's one that you can kind of sort of estimate in your head. Right. A slow motion camera shows that the bat was in contact with the ball for 7 milliseconds. And we're going to look for two things here. The first thing we're going to look for is the impulse imparted on the ball by the baseball bat. And then once we have that, we'll be able to use it to figure out the force. To be perfectly honest, I'm not that interested in the impulse, but this is one of those places where I like to ask an intermediate question just to lead us in the right direction. We can use impulse, and that will be the tool that we need to figure out the force. All right, I'm going to slowly scroll this paragraph of information off of the screen, writing down just the key bits, all the values of the variables. So we've got a mass of 0.145 kilograms. We've got an initial velocity of 38.0 meters per second. We've got a final velocity, VF, of 47.0 meters per second. And we've got a time of 7 milliseconds. Remember, milli is times 10 to the negative third. So we could write it like that, or we could write it out as a decimal if you prefer. Either way, it gives us the same thing. All right, so that's the information that we have that we can use to solve this problem. We know that our end goal is to figure out the force. It was hinted to us that in order to figure out the force, we're going to first want to figure out the impulse. And I guess from there, we can reason. Well, I've got two formulas that use impulse. Impulse is force times time. Well, that won't help us find the impulse if we don't know the force. But once we know the impulse, that will certainly be enough to help us find the force. And then the other thing we know is that impulse is the change in momentum. All right, well, that's great and all, but do we know equations for momentum? Thankfully, in this case, we do. Right? We know that momentum is mass times velocity, which means that the final momentum is the mass times the final velocity, and the initial momentum is the mass times the initial velocity. We were specifically asked for impulse on its own, so I'm not going to try to do everything in one go, but I am going to substitute in those expressions for momentum into this formula, so we can write that the impulse is the mass times the final velocity minus the mass times the initial velocity, and then we can start trying to plug things in, although we do have to be a little bit careful here, because velocity and momentum are vector quantities. And that comes into play here because our initial velocity was coming towards us and our final velocity was going away from us. The velocities are going in different directions. We have to call one of those directions positive and the other one negative. It doesn't really matter which one is which. I'm going to go ahead and define the impulse as being positive by putting some absolute value bars around here, because I don't care which way we end up changing things, I just care that we change things. I think now that I have done this, I probably should have written those in the other order. Let's go ahead and make the final velocity the positive direction, the initial velocity the negative direction. Again, it doesn't matter. I'm going to ignore the sign at the end, but it does matter that they have different signs before I subtract them. All right, so plugging in, our mass is 0.145 kilograms. Our final velocity is 47.0 meters per second. We have subtraction here, but there's going to be a negative that's going to turn it into addition. We have our mass again, 0.145 kilograms. And we have our initial velocity, which is 38 meters per second. From here, I can grab a calculator. Everything can go in one go. 0.145 times 47 plus 0.145 times 38. My calculator tells me that this comes out at 12.325. To get three significant digits out of that, I guess I'll round it to 12.3. It might be, if you are a little bit more careful in how you do this, that you should write it as 12.33 instead. It's one of the downfalls of significant figure analysis is that there are two ways of approaching this problem that will give you slightly different ways of rounding your result. But however we go about it, the units here are kilogram meter per second. Those are the units of impulse. That makes sense. They're also the units of momentum, so it still makes sense in that side. And then from here, we can go back to the other equation. If impulse is force times time, that means that force itself is impulse divided by time. So 12.3 kilogram meter per second divided by the time, which was 7.00 times 10 to the negative third seconds. Always be careful punching scientific notation into your calculator. Depending on how your calculator works, division can do some really weird things. But I end up with 1,760 rounding to 3 significant digits. And my units here are kilogram meter per second divided by second, which is kilogram meter per second squared, which is exactly what I expect from a Newton, the unit that we usually use for force. I hinted earlier that there was going to be conservation in the idea of momentum. If there is no external force, the total momentum in a system will be constant. And it is important here to think about this as the total momentum. So if you have 3 masses, say billiard balls, that are moving in different directions, they may end up colliding with each other, at which point, after some time has elapsed, you will have 3 billiard balls moving differently with respect to one another, but still the same 3 billiard balls. And if you calculate the total momentum, adding the vector momentum of each of the individual parts, you will get the same value. This should make sense if we think about the impulse momentum theorem. If there is no external force, that means that the impulse is 0. So you get that the initial momentum is equal to the final momentum. The interesting thing that we have to add here is, well, what happens if there are more than one object in the system? That nature makes momentum the ideal tool for analyzing the collisions between objects. If we have 2 billiard balls that strike each other and then bounce away, if we know information about how they're moving in the first place, we can use that to predict information about how they will be moving later on. Collisions do get categorized in 2 different forms. Collisions can be either elastic or inelastic. When I think of an elastic collision, I do think about billiard balls. Right? When 2 billiard balls strike against each other, if you can get a slow motion camera to watch them as they go, you will see that they deform a little bit. They kind of shrink in and then bounce back out. And it's that shrink in and bounce back out, which is how the momentum is translated from the before to the after. An inelastic collision, on the other hand, is a case where things collide and stick together. There are not really a lot of everyday examples of inelastic collisions. Not to say that it doesn't happen, it's just a little bit rarer. The classic example that you'll find in textbook problem sets is a train coupling. Right? If you have a train car that is being pushed down the track, and then it attaches itself to the next car and they start moving together as a cohesive whole. That is a collision, and we can model it as an inelastic collision. The idea here of an inelastic collision is that after collision, everything has the same velocity. With an elastic collision, after collision, everything can have different velocities. Let's look at a relatively simple example. We'll look at an elastic collision between two billiard balls. These billiard balls are on a rail so that they cannot move to the side, so we can deal with this in one dimension. We don't have to think about multiple dimensions. But let's say that we have this one. Mass is 0.170 kilograms, and it is moving with a speed, relatively slow speeds. How about something like 7.5 meters per second? It is going to collide with another billiard ball. This one is ever so slightly lighter, 0.160 kilograms. And this one is currently not moving at all. All right, the two billiard balls are going to collide, and then they're going to start moving differently. All right, so they've collided. They've got all these squiggly marks to mark collision on them. And then after the collision, this first one is going much slower. It is going at only 0.5 meters per second. And it's rolling backwards. It collided and then it bounced back. And with that information, we should be able to figure out how fast the second one is going to end up going. We can do this following conservation of momentum. I'm going to go ahead and write down M1 is 0.170 kilograms. M2 is 0.160 kilograms. V10. The velocity of ball 1 initially is 7.5 meters per second. V20, the velocity of ball 2 initially, was 0 meters per second. V1F, the velocity of ball 1 after the collision, is 0.5 meters per second, but it's going the other direction. So we'll go ahead and make that negative. And then V2F is our unknown. Right, a lot of variables going on in this situation. We're going to solve this problem using conservation of momentum. So the initial momentum is equal to the final momentum. The initial momentum itself is the mass of the first thing times the velocity of the first thing initially, plus the mass of the second thing times the velocity of the second thing initially. And then the final momentum, same idea. M1 V1F plus M2 V2F. It is possible that the mass will change in a collision. We're not dealing with that in this particular example, but I did want to stress that it doesn't have to just be the velocity that changes. Anyway, plug in everything and then solve, or solve and then plug in everything. It doesn't really matter all that much. I'm going to plug in everything first because just writing this equation out is messy enough, and I don't want to deal with fractions while I do it. Something didn't work there. Let's try that again. There we go. So on the left-hand side, plug all that stuff into a calculator. You get, I guess we only have two significant digits, so I'll round it and call it 1.3. And my units are kilogram meter per second. On the right-hand side, we're going to have I guess we really only have one significant figure here, negative 0.4 kilogram meter per second plus 0.160 kilograms times V2F. Right. Move the constant over to the left-hand side. 1.3 minus negative 0.4 is positive 1.7. And then get V2F by itself by dividing both sides of the equation by 0.160. Right, I've only got two significant digits here, so I will round that, and I'm going to call it 11. The kilograms cancel each other out, so the units I'm left with are meters per second. The velocity of the second billiard ball is 11 meters per second. All right, we've covered a lot of ground in this video. I think that's probably far enough for one lesson. So I'll wrap up with that. As always, thank you for joining me, and I'll see you next time.